Hello, everyone. My name is Jose Aguirre. Sorry about this delay. We had some technical issues and we were not able to go live before, but let's start over here in a second. Let me go through the slide, and I didn't want to waste more time. So let me just go back and go to the first slide. 1 second. All right. Okay. So, well, my name is Jose Aguirre here from the TIBCO team. Welcome to this July live session for Dr. Spotfire. I'm Jose Aguirre from TIBCO. I will be your host for this session. I'm here with Sweta, and Sweta, you want to greet our audience?
Yeah, hello everyone. I'm Sweta Kotha, and I'm a data scientist here. I'm working alongside Jose.
Okay, I'm going to go through some introduction slides real quick before we get started. So our motto here is that learning is driven by answers. Learning is not driven by answers, but by questions. So let those questions drive your learning. Keep the questions coming through the chat. We also have a YouTube channel. These channels are streamed live through YouTube, but they will still be available in case you miss something. If you want to come back at a later time to watch or have more questions or comments. Then we have our data science channel as well, where you can also watch previous Dr. Science topics with Atheer Alattar that held on the third Wednesday of every month at 9 a.m. Pacific. And he's talking about, he talks about a wide range of topics such as AI applications, low code, no code, machine learning, and many more. Check it out. We also have a new community coming up. We're working for you guys to have a better community experience. So stay tuned for the new TIBCO community, which will be launching soon. Starting in July 8th, the current community will be read-only, so we will not be able to ask or answer any questions until the new community is released. And the feature session today is model evaluation and explainability. So model evaluation and explainability is crucial in the data science pipeline to assess how models are learning or performing and to identify any model biases. Sweta will be showing our Spotfire templates that evaluate regression and classification models and explain model prediction using the popular LIME and SHAP algorithms. So what's a model evaluation? Well, model evaluation is the process of using different evaluation metrics to understand a machine learning model performance, as well as its strengths and weaknesses. Explainability, on the other hand, or explainable AI or explainable machine learning is artificial intelligence in which the result of a solution can be understood by humans, in contrast with the concept of the black box in machine learning, where even its designers cannot explain why AI arrive at a specific decision. With the explainability, we humans can understand these AI results. And just to have everyone on the same page, and for those aspiring data scientists, let me touch on the concept of machine learning model. A machine learning model is a file that has been trained to recognize certain types of patterns. You train a model over a set of data, providing an algorithm that can be used to reason over and learn from the data. Once you have trained a model, you can use it to reason over the data that it hasn't seen before and make predictions about the data. For example, let's say you want to build an application that you recognize users' emotion based on their facial expression. You can train a model by providing it with images or faces that engage with a certain emotion. Then you can use that model in an application that can recognize any user's emotion. So TIBCO model evaluation templates make it easy for data scientists and business analysts alike to easily view models, model outcomes, assess, fit, compare parameters, subspaces, and Sweta will be talking more about these while demonstrating some cases using TIBCO Spotfire. So please send us your comments or questions through the chat as we go live. But if you're watching this video later, you can still comment, and someone from the community or TIBCO team will get back to you. So back to you, Sweta.
Thanks, Jose. So let me go ahead and bring up my screen. Okay. So if you recall, a few months ago in our December session from last year, as well as our January session from this year, we had two sessions on Intro to Machine Learning. So one of them focused on regression methods and the other one focused on classification methods. Our model evaluation component today is going to be some sort of extension to those. So we're going to talk about how we can evaluate regression and classification models. So let me go ahead and show you, first of all, where you can find these assets that we're talking about, or if you want to follow along. Again, on our TIBCO community page, we have a wiki page called Model Evaluation Templates for TIBCO Spotfire and TIBCO Data Science. This is going to walk you through exactly what we're going to see today. And if you go all the way to the bottom, you'll see the two DXPs that I'm going to be walking through right now. So again, let's go ahead and focus on the regression case first. So again, regression machine learning methods refers to any sort of algorithms that predict some sort of numerical value. So we have different types of machine learning models that do this. The ones that we're actually going to be working with today are neural network, random forest, and linear regression. So these can all work in the regression scenario. And we're going to already assume that we have these models trained and that we have some sort of these models trained and that we use these models to score new data. So these models were taken and they scored new testing data that we've never seen before. And now the question comes to mind, well, what do we do after that? How do we choose one or more models to continue with forward, whether it's running it through prediction, whether it's further evaluating it, etc. So the way that this DXP is set up is that we again ran 3 different types of models on a data set. It's the UCI energy efficiency data set. So this data set uses various types of features such as surface area, wall area, roof area of buildings, and it uses these to try to predict its energy efficiency. So that's measured by these 2 columns called heating load and cooling load. So we're just going to fixate on heating load today as our predictor or target column. So you'll see that in this left text area here, we specified that our target is heating load. And then what we went ahead and did is trained these different types of models using Spotfire data functions. So you see here that I already have a linear regression, random forest, and TensorFlow model. Well, and this template actually says it itself, but these model outputs, the model outputs we use can be either from Spotfire or TIBCO Data Science, but we're going to focus on the Spotfire side today. So we have these 3 models trained to predict heating load. And the first thing that we actually want to do is evaluate how these models have been trained or are performing. So let's go ahead and select all 3 of these models. And you'll notice here that the scatter plot is updated. So this is the predictions from the models on this y-axis against the target column, which is heating load. Now, it's very actually important to use a combination of metrics as well as visual analysis to be able to evaluate models, and you'll see why. What we're looking for here is that there's going to be a line called y equals x. This is essentially the middle line, and this is where the predictions match up with the heating load. So you can see this dotted black line right there. So in the case of this neural network, you see that most of the predictions, each circle represents one type of prediction, is actually pretty close to the actual value since they fall along this line. Now, if I add on the random forest, which is going to be these blue predictions, you'll see that that's still maintained, that we have 2 models where the predictions match the actual values pretty well. Lastly, if I add on the random forest, you'll see that it kind of deviates from the actuals a bit. The predictions deviate from the actuals. And you notice this because some of these values stray away from that 45-degree y equals x line. So for example, we have these values right here, or like these ones right here. And the reason that this is important is because for different types of models, it could indicate to us that there are subsets of the data that our model is not able to predict well on or needs to be further trained on. So using these types of scatterplot analyses could actually identify model biases. In addition to this chart, the scatterplot right here, we can also look at the histogram of residuals. So a residual is a distance from a prediction to the observed value. So in this case, if I fixate on this one data point here, the residual is going to be the distance from this point to this line. And now when we have a scatter plot of the residuals, we ideally want it to be, either normally distributed or not too spread out. But we see here that the linear regression one, again, is quite spread out to some degree compared to the other two models. So these are just some visual tactics that we've used so far. In addition to that, we can also calculate different types of evaluation metrics. So that is what this DXP includes. There's this function called evaluation regression that we run in this DXP, where you specify the target column, heating load, as well as the different model predictions. So this is going to be taken pred neural network, predictions from the random forest, and predictions from the linear regression. And then it's going to go ahead and calculate these different evaluation metrics.
So, Sweta, can I ask you a question?
Yeah.
Which model is best? Is this the one that has everything aligned, the x equals y line, or how do you see which model is more accurate than the other? Of course, you can say by looking at the line which ones are more aligned. But in this case, for example, the random forest, you have some spread out. Is that something to be concerned, or you have to further train the model to see?
Yeah, so this is a linear regression model, and in comparison to the other two, it looks like the other two models have predictions that line up more closely with the actual values. So we could take that to mean that they are better performing models. We could also use this evaluation metric chart, and let's just fixate on two metrics, the mean squared error, the mean absolute error. You'll see that they are much lower for the neural network and random forest than the linear regression, which in this case, we would want to minimize those two types of errors. So these, in hindsight, could tell us that the neural network and random forest are the better performing models. A lot of times people might use one or more models if you want an ensemble of models to be able to evaluate. So really, in this case, it could be either or, I'd say, for the neural network or random forest.
All right, thank you, Sweta.
Mm-hmm. Yeah, so this is what we have for our regression DXP template. Over here, we ran ahead and said, since the random forest is one of the top performing ones along with the neural network, we went ahead and also got the feature importances from it, so you can see how the different features are weighted in the model. Now, the other template that comes from that community page is our classification template. So this one is now focused on classification machine learning algorithms. So we have the same data source, the UCI energy efficiency. In this case, we specified what we went ahead and did is we transformed heating load to take in to some type of binary outcome. So instead of having numerical values for heating load, we now have either high or low. So here we specified, here we want to specify our the target column. In this case, it's just called classification because that's what we call this high-low label. And we want to say what the positive label is. So in this case, we're gonna say that we're interested in predicting high, or that's what we want to base off this analysis from. And again, we select the different sorts of model predictions. And here we can actually also have a probability cutoff, because with any type of classification model, you're going to get different probabilities for each class predicted. So for example, you're going to say that the logistic, so any one model might say that this is high or low with 0.5%, or it might say this is high or low with 0.4, 0.6%, etc. So we actually discussed this in our classification Dr. Spotfire Intro to ML session, where we talked about how you can use ROC curves to evaluate the best model. So essentially, if we're looking for any curve that falls above the other and that falls above the others, as well as this baseline dashed line, and that is closer to the upper left corner. So here we see that the random forest is the best performing model based on the AUC ROC curve. We can also use confusion matrices in order to tally our predictions versus observed. So unlike before where we had a scatter plot, we now have this breakdown of high-low frequencies, and this is how we look at our predictions versus actual values. And of course, we can always look at model accuracy too. That's a very naive sort of metric, but it could be something that you could further dive into. And then we have our metrics itself for AUC, accuracy, and F1. So these are our regression and classification templates that, again, are on our TIBCO community page. For more questions, we could reference this wiki page or one of our previous sessions on classification and regression for more of the inner workings on what we did prior to these evaluation steps. So with that said, I'm going to go ahead and switch over to the other half of today's component, which is going to be on model explainability.
Okay, so we did the model evaluation, and now we're going to do the model, the explainability.
Mm-hmm. Yeah, so let me go ahead and start off with a few slides. So Jose actually briefly mentioned that we're going to be discussing two sets of algorithms that are really the main standard or ever popular for model explainability right now. They're called SHAP and LIME, and both of these were released in around 2016 or 2017. So what we went ahead and did is created a set of Python data functions to perform model explainability via the SHAP and LIME algorithms.
And these data functions are available in the community. I can download those data functions and use them.
Yeah, yes. So actually, you can go ahead to our TIBCO community, and on our data functions page, or via this link right here, you can find our model explainability Python toolkit for TIBCO Spotfire.
Awesome.
And this is the exact toolkit that I'll be demoing right after.
Okay, perfect. Thank you.
Yeah. So that's where you can actually find the template. And let's go through a quick overview of what exactly LIME and SHAP are. So SHAP is based on this concept of Shapley values, which comes from cooperative game theory. Essentially, it translates primary game theory questions into model explainability standards. So for example, if we're interested in the outcome of a game, this translates to a model prediction. We have a variation of players in this game or in this environment, and we have different types of features. We're interested in how much each player might contribute. Likewise, we want to know how much each feature contributes. And this all comes down to Shapley values to measure this contribution. Now, SHAP and LIME are both actually very complex algorithms. So we're going to try to simplify or at least present the high level ideas that you can take away from these algorithms, just to give some sort of introduction. So what SHAP essentially does is it quantifies each feature's contribution to the model prediction. Or actually, why don't I go ahead and take a few steps back? So let me go back to this first page here, and I want to try kind of emphasize like why we're interested in model explainability. And Jose already did mention this a bit. So there's a push for this concept of explainable AI, because when you think about it, a lot of machine learning models are used for making high risk or quite complex decisions. It could be something such as should a bank lend a loan to a user? So, there's a lot of intricate factors as well as high risk factors for both the bank as well as a user in this context. And listening to a model itself that gives you no explanation as to why it made a decision. So let's say we had a machine learning model that said yes or no, that this user should get a loan from the bank. Well, if the model went ahead and said, no, we do not want to you should not give this customer a loan, and the bank tells that customer that, the customer might come back and ask, well, why? Why shouldn't I be able to receive a loan? And just based on this yes-no model itself, we have no way to actually explain to them why we made that outcome. And it could be actually, there's no credibility to the decision that we made. So that's why there's been this push for explainable AI that tries to unravel or remove this black box layer, which behind a lot of these popular machine learning algorithms. And so what LIME and SHAP do essentially is that they try to explain a model's predictions. And you'll see that what SHAP does is it tries to quantify each feature's contribution to the model prediction. So what it's doing is it takes the empty set. So it doesn't consider any features at all. And then it goes ahead and slowly adds one feature at a time to test out different combinations of features and how this affects the model's predictions. So in the end, we have ways to say that this one feature here, let's say like a customer's time with a certain bank or their history. We want to be able to say how this history contributes to the model's prediction. So SHAP is pretty efficient. It doesn't train all types of potential models, but it does require incoming training data to test out different types of subsets.
Okay, that's really great, Sweta. We have a question from Chris Brown. Let me put it on the screen. It says, is there any way to access the example template with Spotfire version 10? Because it looks like it was created on version 11 and it's not available on version 10. So they might want to download that DXP. Let me see if I can answer that question for Chris. We will see if we can put it back to version 10 or the earliest version possible and make sure that the template still works as expected in other future versions. Is that right, Sweta?
Yes, I think that's right. So we tend to use Spotfire 11 just because we have access to mods, but this template doesn't include any mods, so it can be theoretically open in prior versions.
Excellent.
Yeah. Likewise, just like SHAP, I would want to give a quick introduction to LIME. So this is the other algorithm. So what LIME does is that it fixates on any one point that we want to explain. So let's say that we have prediction for this new customer. So it takes that point and it goes ahead and it synthesizes or makes new artificial data around that point. And it trains a model. It specifically trains actually a linear model on this artificial data. So it's training a model on a smaller subset of the data. And the reason that it's doing this is being able to test out how different types of features contribute towards that overall prediction.
Okay, so the little blue dots are synthetic data near the point of interest. That's
yes. So that's the artificial data that LIME is creating. It's fixating on this one red point here, and it says, in order to explain this prediction, what we want to do is go ahead and make artificial data around it and try to train a new model based on these permutations of the data.
Okay, and you can do the same process for more points, right?
Yes, yeah. And the reason it's doing this is because it's training a linear regression model, to be specific. Linear regression models are highly explainable just in the way that they're actually set up. So compared to more complex models like the neural network or a random forest, if we try to train a linear regression here, it's very easily explainable. So LIME is essentially trying to, I don't want to say replace, but trying to find a linear regression model that can work like any of the models, like any of the model that you actually used to create these predictions.
Mm-hmm.
So let me go ahead and actually show the template for this. So this is the template that's going to accompany the model explainability data function. So here you can see that we're actually working with the same data set, the UCI energy efficiency data set. Except in this case, actually, we use cooling load as the predictor. No real reason to that. We just ended up using this one instead. And the first thing I'll do is go ahead and walk through how this data functions in here are set up. So just like the evaluation template, we had to train some sort of model. So just for ease, we just picked one model. Here we trained a random forest on this UCI energy data set, and it's predicting cooling load. And now once we have those models, we have these 5 different explainability data functions. So we actually have 2 for LIME and 3 for SHAP. So it looks quite complex, but let me break down how these are set up. So let's focus on the case for LIME. So the first thing you need to do once you have your model is run this function called LIME create explainer. So the reason that we actually separated LIME into 2 data functions is because LIME and SHAP work interestingly in that they require the training data. Now, this could potentially cause problems because there are situations where you won't always have access to your training data, especially in like a front end analysis. Your data might be stored elsewhere. And LIME and SHAP actually also require access to the model itself, at least via these Python implementations. So here in this create explainer, you have to pass in the data function or pass in the training data. You have to specify the target column. In this case, it's going to be cooling load. And then you have to, again, say if it's regression or classification. Here, we're going to focus on regression. So once you do that, you create this explainer object that LIME needs. So here, if we go to the data functions workflow, you can see that the result of LIME create explainer is this explainer binary object. So that's the only thing that's created. Now, the real function that we're, or not the real function, but the function that we actually use to explain any one prediction is going to be LIME explain single prediction. So it takes in your testing data, or it takes in technically like one column where you made some sort of prediction. So it takes in a prediction column. And it, again, takes in the task, takes in this explainer object that was created from the LIME create explainer. And here it's taking in the model. So you saw that the previous data function took in the training data, and this one has to take in the model. And using that, what it's going to do is, if you select on any one instance from the testing data, you're going to see that the LIME explanations are now explaining this prediction. So we have this one instance from our testing data where it predicted that the cooling load is 23.77. And now LIME has just updated to explain that prediction.
I have a question here from a LinkedIn user. It says, why creating artificial points instead of using the real data that led to this prediction? Remember those that slide where I asked about the blue points? I think he's referring to that. Yes.
Yeah. Yes, because LIME is it's trying to, again, fit a linear model in the small space right next to this point. So it's going to be testing out different combination of data points, because again, the data set you have is not going to represent all combinations, and it's also testing out different combinations of features too. So it's trying to understand the data in this closed space right here, fitting a model through that, exactly.
It's just a small data set, so if you apply the same algorithm into each point, it will create more synthetic data to come up with that line, and if you put them all together, it will kind of follow the same pattern.
Yeah, so we want to, like it says here, understand the flatness of train essentially a straight line fit or flat line model through the small space, not across all our data.
Okay, perfect. Thank you, Sweater.
Yes. So yes, we just covered how the LIME data functions are set up, and now the SHAP data functions actually happen to be set up in the same way. So we have SHAP create explainer, which you're going to have to run first. In this case, it takes in the training data as well as the model. Then we have SHAP explain single prediction, just like we had LIME explain single prediction. So it takes in one value from your one observation, one row from your test data, and then it's able to explain that single prediction. And in the case of SHAP, actually, it also can do this thing called explain batch predictions. So it can take in multiple predictions and be able to explain them. And this takes in, again, a similar type of input to the other explain data functions. So this is how the data functions are set up. Now we're going to take a look at how we can actually interpret the visuals that we set up here. So we'll go ahead and start off with LIME. So this is the visual that we had from LIME explanations. So again, this is working on this one row observation. It's explaining this prediction right here for this row. So if we go to, LIME explain single prediction, you'll see that one of the results here, LIME single explanation, is going to be this data table where we have the features that are discretized, and we have their score and their order. So this is what we used to create this bar chart over here. So you'll see that we have our features in a certain order over their scores. And again, since I told you that LIME is fitting a linear regression model, these actual these categories, or these values, excuse me, are actually just going to be the coefficients from the linear regression model. So here, when we have a value that is right of this line, that indicates that it's positive. When we have a value that is left of this black line, that indicates that it's negative. Or here it's in light blue, positive is in purple, and negative is in light blue. So what this actually is telling us, since it's the coefficients from the model, from the linear regression model, is how any one feature can increase or decrease the prediction. So here we say that overall height, when it's in this discretized category of between 5.25 to 7, it tends to increase the predictor. It tends to increase cooling load. On the other hand, for this one prediction, glazing area tend to decrease cooling load. So this is what these different values are telling us, how any one feature is increasing or decreasing the predictor for this prediction.
Okay, we have a question. It says, how an explanation is expressed with the weighted features? Is it probabilistic or explanation?
So can you repeat that, Jose?
Yes, concretely, how an explanation is expressed with the weighted features. And then, is it probabilistic? Is it probabilistic explanation?
So it's not necessarily probabilistic. In this case for LIME, actually, it's very relative. All it's telling us is that this one feature tend to increase the predictor. And it also quantifies to some degree. It tells us whether it's increasing or decreasing the predictor, and also relatively how much so is it doing. So here, all we can say from LIME is that overall height tends to increase cooling load, and it tends to increase it the most compared to at least other features. But now in the case of SHAP, actually, we can quantify that specific effect. And you'll see what I mean here in a second. But we can actually go ahead and talk about SHAP real quickly.
Okay.
So to talk about SHAP.
Yeah, go ahead.
Okay, so I do want to get back to that question, and I think you'll see here in a minute what I mean. So LIME is very relative in terms of how the features are contributing towards the model prediction, but SHAP has this advantage where it can quantify that specific effect. So for here, the color scheme means the same thing. For any one feature, we see that it is negatively or positively increasing the predictor. But in the case of SHAP, we can actually quantify it. So it says for that, for the single prediction right here, SHAP is telling us in this bar chart. This bar chart looks similar to LIME again, but it's telling us that the model, it's telling us that the feature glazing area is decreasing the prediction by -3.9, while the feature overall height is increasing cooling load by 3.74. Relative compactness is increasing by 2.06. So unlike before where it's relative, here we can quantify that direct effect.
Oh, that's very interesting. So LIME is telling whether it's increasing or decreasing. It's more general, but the SHAP algorithm is more quantitative, and it will not only give you if it's increasing or decreasing, but for how much. Is one algorithm better than the other, or do they complement each other just to validate the result of both?
Yes, you can think of them as complementing each other. Data scientists might have their preference for one or over the other, but it's nice in a way to run both of them, because you'll see here, look at the top features here: overall height, glazing area, relative compactness, and you'll see that those from LIME match up those from SHAP. So that's validating in some sort of sense, right?
Okay. Yeah, we have another question related to that. It says, okay, identifies critical factors and a relative comparison of their it identifies critical factors and relative comparison of their impact on the prediction. It's a kind of a question at the end, question mark at the end.
Yes.
Yeah.
So it's telling you for any one prediction, it's trying to break down how this prediction was made by how the different types of features are contributing towards that prediction.
Okay. And then another question probably related, it's does it happen sometimes that the LIME and SHAP they contradict each other, or they're pretty similar most of the time?
Oh, it does happen. And again, this just has happened with us playing around with these templates and learning more about the algorithms themselves. So notice that that can be something to be wary of, right? If you have either these two algorithms that differ on how they are explaining a single prediction. So you might also wisely put you might also wisely distrust these algorithms to some degree. So one thing that I wanted to actually say at the end that maybe I'll just say now is that we're using these algorithms in order to unravel black box machine learning algorithms, but it's kind of contradictory because, again, on top of these ML models, we're now putting on LIME and SHAP, which are, again, complex models themselves. And although they do try to break down these black box machine learning models, we might be going down a rabbit hole in terms of how many layers do we have to dig through. So there is still reason to be skeptical, or I'd say wary of explanations, as you should be from any type of AI algorithm.
Mm-hmm. Yeah, so a lot comes also with the human interpretation of the results to make a decision.
Yes. So I'm going to talk a little bit more about drawbacks to these at the end. I want to make sure that we talk about the visuals for SHAP and LIME. So we already covered for SHAP and LIME this basic bar chart. I'll just say actually real quickly that on the first page, so LIME and SHAP can both be displayed by this bar chart where you have the feature order over the score or the SHAP value in the case of SHAP. SHAP can also be made into this waterfall chart that we have here. So all this is doing is taking the same chart on the right and just adding up the cumulative effects to tell you in the end that this value 0.21 is the difference from the average value of cooling load. So for this model prediction, it is 0.21 higher than the average value of cooling load in the training data set. So again, this is just the same way to represent this bar chart, but just again in a waterfall chart.
Okay.
And lastly, with SHAP, I mentioned that we also have this data function for batch explanations, because instead of just explaining one prediction, it can take a batch of predictions, so multiple values from this data table, and it can create this chart over here. So what it's doing is that each one of these squares represents a prediction, and those that fall towards the right of this black line tend to increase the predictors more, and those that fall towards the left of this black line tend to decrease the predictions more. So it's relative. And then a reddish color indicates a higher value of that feature, while a bluish color indicates a lower value of that feature. So let's just look at overall height, for example. It's telling us that higher values of overall height really tend to increase cooling load, while lower values of overall height really tend to decrease cooling load.
Interesting.
Mm-hmm.
Let me see if I have any more questions here. Oh, yes, we have one. It says, confidence interval. Are they important in this evaluation? So is the confidence interval important in this evaluation?
No, so we don't actually use confidence intervals here for SHAP. For LIME, you technically, I guess, can, because they are, again, these bars are essentially the beta coefficients from the linear regression, but we don't extract these from the LIME algorithm.
Mm-hmm.
Or the LIME algorithm, sorry, doesn't supply those to us easily.
Right.
Yeah, and I think I'll go ahead and touch up real quickly on, I already mentioned how these are set up. So for, again, LIME and SHAP, we have two columns on the y-axis that talk about the feature, as well as how they should be ordered. So first you specify this order, which is represented by this number here. And then we actually have the feature name. And then it's on the x-axis, we're going to have the score or SHAP value. And then, of course, for SHAP, we could also just make that same thing into a waterfall chart.
Okay.
And lastly, I think I just want to go back to, the drawbacks or caveats. I already mentioned that, there are times you might want to be very wary, again, if LIME and SHAP tend to disagree. Also, consider how your model was trained. Has your model been fully trained? Does it make sense that it's sufficient to use in a prediction scenario? A couple other things to mention is that LIME and SHAP tend to work on numerical data, so you have to be careful of how you encode them. LIME specifically, it doesn't make sense to put in one-hot encoded features, because when you perturb those, because when you perturb or create artificial data in LIME from that, it's not going to make much sense to evaluate. And one thing that could also be helpful is to put in random features into your model. So for example, if you just create a random column and throw it into your model, you can see perhaps where that column might appear in this distribution of features. And that can give you an idea to say, since this is random, anything below it, I don't trust, or might be kind of junk. And anything above it, you can maybe take with more of a, take to be as more realistic for true feature predictions.
Okay, well, these bring these questions up from Neil Canungo. It says, how easy is to use or own the data in these templates? So I'm to complement to that question, do we have to clean the data, make sure everything is tidy and everything, or how does that work?
Yeah, so you do need to clean the data to some degree, because again, you want to train, because again, the prior step to LIME and SHAP is that you do need to train a machine learning model. So we have data functions available on our community for imputation and transforming categorical variables. And then you can, once you've cleaned it to some degree, you can then use any one of the machine learning data functions. But you do still need to take those steps. You know, you can't just throw everything into these explainable methods. It's not going to work like that.
And then using these templates is just straightforward, right?
Yes, yeah. Like I said, you can reference this session here in terms of you know, the steps that we did to actually run the different data functions. We have wiki assets as well as wiki pages that you can also ask questions on.
Okay, and that's perfect. That's all well documented in the wiki pages where you can download the templates. Perfect. Well, if we don't have any other questions, our next session will probably cover some of the features released in TIBCO Spotfire 12. So stay tuned and don't forget to share, like, and subscribe for updates. Thanks. Thank you, Sweta, for great explanation. And thanks, everyone, for joining. Have a great rest of the week.
Thanks, everyone.
Bye-bye. Oh, we have one question. We have one question right here before we go. Just in time, it says, are those models already used in pharma companies? Do you know?
So, I mean, these models can be generic to any use case. I can't think of a pharma-related use case that we had recently, but of course, these can be applied to that strategy, right? So it can work across any industry, these models.
Excellent. Well, we are running out of time. I'm sorry for the delay again. We will keep. We're open to receive more questions, and if you have any other comments or questions, just feel free to put it, and we will get back to you next time. Thank you, everyone, and bye-bye.